So remember, the speed of a mechanical wave depends mainly on two factors: the strength of the restoring force, which tends to bring the oscillating particles back to equilibrium, and the inertia, the part that the particles resist being brought back to equilibrium. So for a transverse wave on a string, the wave speed was equal to the square root of the tension force divided by the linear density. So again, that tension was the restoring force, and the linear density was the inertia. So when we're looking at the speed of sound, in this case in a fluid, the restoring force is represented by how easily the fluid is compressed. And remember, that's what the bulk modulus represents. The higher the bulk modulus, the harder the fluid is to compress. And the inertia is represented by the density of the fluid. So you can see for a fluid, the speed of sound is this equation, the square root of the bulk modulus divided by the density. So it's similar to the square root f over the linear density for the transverse wave on a string. It's just the square root of the restoring force component divided by the inertia component. So for a solid, the speed of sound in a solid, we have a similar equation, except with this y, which is Young's modulus, which is basically the same thing as bulk modulus, but for a solid. And for an ideal gas, which is, gases are fluids, but for an ideal gas, we can write another equation, which is this, where this thingy is something called the ratio of heat capacities. Don't worry about this too much. And then times the universal gas constant, the Kelvin temperature over the molar mass of the ideal gas. So from these equations, you can see that the more dense something is, the more dense the medium is, the slower sound travels. But we know that sound travels faster in solids and liquids than gases. So that's not because solids and liquids are more dense than gases. Density actually decreases the speed of sound. That's due to the other component, which is how hard the medium is to compress. Solids are a lot harder to compress than liquids or gases. So this component increases, and the speed of sound is faster. So the harder something is to compress, the faster sound will travel through it. And to kind of visualize why this happens, imagine you have two springs, and one spring is stiffer than the other. So obviously, when you compress the springs, the stiffer one will be harder to compress. But when you release it, the stiffer spring will bounce back faster than the other spring. So the stiffer spring bounces back faster, so therefore it can transfer energy faster once you release it. So the harder the medium is to compress, the faster it will transfer energy. And remember, waves are just transporting energy. So that's why waves travel faster when the medium is harder to compress, and slower when it's more dense. Because the more dense something is, the more inertia it has, and the harder it is to get the particles to be oscillating in that wave. So now we're going to look at the energy in these sound waves. So remember, for a mechanical wave, the intensity is the average power divided by the area that that the wave is spread out over. So to find this equation for a sound wave, we can just take the equation we found for the pressure fluctuation times the equation for the velocity of the particles. This is not the wave speed, this is how fast the particles are moving left and right in the wave. So pressure is force over area, and force times velocity, we know that's power. So when we multiply these, we'll get power over area. And so this is what these two equations multiplied And then remember, for the intensity, we have the average power over the area. So the average power, the average of this sine component is 1/2. So we get that the intensity is, this expression. And we can, write it in another notation, substituting in, omega over the wave speed for the wave number. And, this thing, we just found that the speed of sound is the square root of the bulk modulus divided by the density. So, in the end, we get this equation for the intensity of the sound wave. And again, this shows that the intensity is proportional to the square of the frequency and the square of the amplitude in a mechanical wave. Now, this is consistent with what we found earlier for other mechanical waves. So we can also express the intensity in terms of the pressure amplitude. And basically, this shows that if we have two sound waves with the same intensity but different frequencies, this omega part, then they have different displacement amplitudes, how much the particles are moving left and right, but they'll have the same pressure amplitudes. So we can also define something called the sound intensity level, which, it's a logarithmic scale to represent how the intensity of a sound wave as it travels. So to get the sound intensity level, we take 10 times the log of the intensity of the sound wave divided by this reference intensity, which is 10 to the negative 12th. So again, you take the intensity of the sound wave, divide it by 10 to the negative 12th, take the log base 10 of that, multiply by 10, and you get the sound intensity level, which is, the unit of that is the decibel.